We have an A-level question that says, the velocity of sound wave through a metal rod is dependent on the density and the Young's modulus of the material. So let's go ahead and represent that with an equation. Velocity depends on the density and Young's modulus. The extent to which the velocity depends on these two parameters is not given. So we represent that with an unknown. We say that velocity depends on density raised to exponent of x and Young's modulus raised to exponent of y. So our task here is to find these two unknown. Now, how do we do that? We're going to use the method of dimension analysis to find that. So let's go ahead and find the dimension of each of the parameters. The dimension of velocity is Lt to the power of -1 because velocity is meters per second. The dimension of density is ml to the power of -3 because density is mass over volume. Dimension of Young's modulus is same thing as the dimension of pressure. Why? Because Young's modulus is stress over strain, that is tensile stress over tensile strain. Note that tensile strain does not have a dimension because tensile strain is extension over length. So both extension and length, they have the same dimension, that is dimension of extension is length, dimension of length is also length. So this cancels this, which means that strain does not have a dimension. Tensile stress, on the other hand, is force over area, and so pressure is also force over area. So it's going to have the dimension of pressure. Pressure is, force is mass times acceleration, which means that the dimension for force is mLt to the power of -2. Dimension for area is L squared. So the dimension for stress is going to give us mL to the power of -1 T to the power of -2. So dimension of Young's modulus is mL to the power of -1 T to the power of -2. Now that we have found the dimension of all the parameters, let's now apply it in our equation. We have that velocity depends on density to the power of x, Young's modulus to the power of y. Now, we are looking for an equation that connect them, formula that connect them. So we must change this variation sign to equal to. When we do that, we have to introduce a constant. So we'll say V equal a density to the power of x, Young's modulus to the power of y. Now let's slot in the dimension of each of them. The dimension of velocity is Lt to the power of -1 equal to, the constant does not have a dimension, so we leave it that way. Dimension of density is mL to the power of -3. So since as exponent of x, we multiply all through all the exponent by x. And that of Young's modulus is mL to the power of -1 T to the power of -2, and the exponent to y, so we also multiply this by y. Now when you have exponents this way, what you do is you multiply through the exponent. So we have Lt to the power of -1 equal to k. Now m as exponent of 1, so 1 times x is still going to give us x. So it will be m to the power of x, L to the power of -3x times m here as an exponent of 1, so 1 times y is going to give us y still. So m to the power of y, L to the power of -y, then t to the power of -2y. The next thing for us to do is to combine similar terms. So Lt to the power of -1 is going to equal k. We have m to the power of x multiplied by m to the power of y. That should give m to the power of x plus y. And for L, we have L to the power of negative 3x multiplied by L to the power of negative y. That should give L to the power of negative 3x minus y. Then for t, we have only one t. So we have t to the power of negative 2y. Now the next thing for us to do is to compare the left-hand side and the right-hand side of the equations. On the left, we have only L and t. On the right-hand side, we have m, L, and t. You can see that m is absent on the left-hand side. Whenever an exponent or whenever a parameter is not present on its side, what you do is take that parameter and give it an exponent of 0. So on the left-hand side, we are going to write m to the power of 0. We have not changed this equation at all because m to the power of 0 is 1. So it's like we are multiplying this equation by 1. We only did that so that in this side, right on the left-hand side, m to the power of 0 or m is going to be present on the left-hand side also because we want to compare. So whenever an exponent is absent on its side, you give that parameter an exponent of 0. Now, let's begin to compare. Comparing for m, that is comparing for mass, on the left-hand side, we have m to the power of 0. On the right-hand side, we have m to the power of x plus y. So m cancel m, 0 is going to equal x plus y, which is the same thing as saying x equal negative y. So stop here and make this our first equation. So let's say this is equation 1. Now let's compare for the other ones. Comparing for L, we have on the left-hand side, L to the power of 1 equal to, on the right-hand side, we have L to the power of negative 3x minus y. So L cancel L, we have 1 equal negative 3x minus y, which we can say this is the same thing as 1 minus or 1 plus 3x equal negative y, or we say y equal negative 3x minus 1, right? So we can make this our second equation. So this is going to equal equation 2. Now comparing for t, on the left-hand side, we have t to the power of negative 1 equal, on the right-hand side, we have t to the power of negative 2y. So t cancel t, negative 1 equal negative 2y. Negative cancel negative, we have 1 equal 2y. So divide both sides by 2, y is going to equal 1 over 2. So y is equal half. Let's write it somewhere here. Y is equal to half. Now we need to look for x. We can look for x by using equation 1 because equation 1 says x equal negative y. Let me clear up some space so that we can look for x. So from equation 1 says x equal negative y. That means x is going to equal negative 1 over 2 because we have that y equal half. So we have both x and we have y. X is equal to negative 1 over 2. Now let's substitute that into our equation. Our initial equation is V equal to K, density to the power of X, Young's modulus to the power of Y. So this becomes V equal to K, density to the power of negative 1 over 2, then Young's modulus to the power of half. When we have a negative exponent, this is the same thing as K 1 over density to the power of half multiplied by Young's modulus to the power of r, which is the same thing as k multiplied by 1 over square root of density, right? P to the power, or density to the power of r, is something as square root of density multiplied by square root of Young's modulus. You can combine both and say k is equal to square root of Young's modulus or square root of density. So the equation connecting the two is k square root of Young's modulus over density, right? If you are familiar with sound wave, velocity of sound wave, you should know that this is a correct formula. The formula for calculating velocity of sound wave through a material is equal to modulus of elasticity of the medium over density. So we have derived the formula connecting them in dimension analysis.